So, like I said, today we're going to deal with annuities and how that works. So we've dealt with 2-0 through all the interest. And if you remember, I call that a lump sum formula, where all of the interest A equals P, 1 plus R over M to the MT. That's where you put one amount in, and you let that amount gain interest over time. All right, so that's the basic formula that motivates, the first 2/3 of the chapter. And then the last third of this chapter is about annuities. All right, and annuities are also tied to how loans work, and then we'll talk about some observations that we have made about why rich people may get richer. So before we get started with annuities, I do want to point out that the test is this week. All right. So the test is this week. You're going to have to take the test. It has a little bit of a lockdown browser. You're going to, click on that test. This is a much slowed down version of my computer. I don't know why. You have to click on that test, take it. Unlike the homework, you only get 2 attempts on the test. And each attempt is time limited at 4 hours, just so that if you start taking it one day, you don't come back to it the next. All right. Most of the time, the test takes a lot less than 4 hours. Should only take you probably about an hour, I would assume. So, test usually takes about an hour. Time limit's at 4 hours, so people don't, pick it up the next day. The questions on this test will all come from the previous homeworks for chapters 1 and 2. So you'll see there's a practice test. There's no practice test in that spot on the in Moodle. So if you click on that, there's nothing in there. And the reason there's no practice test there is that the practice test is basically just the past homeworks, all right? All of the questions on the test will be just like the ones from the past homeworks, except I've adjusted the numbers and things like that. Does that work? So, there we go. All right. So, without spending too much more time on that, let's deal with annuities. So most people don't have a huge amount that they can just put in and gain interest. All right. So, for instance, when people save for retirement, they don't just lump sum put in $1 million and let it gain interest for, 30 years. Nobody has, the vast majority of people don't have $1 million to, put in an account and just let it sit. So when we save for retirement, oftentimes we put in smaller amounts over time. So maybe you put in $1,000 a month or $500 a month or something like that. Now, when we do this annuities calculation, we're going to make a few assumptions. One of the assumptions is that I'm going to put in the same amount from month to month or from year to year. The other assumption, just like we did in our previous work, we're going to assume we get the same interest rate from month to month and year to year. If you put it in the stock market, you know that some years are going to be higher rates than others. Some years might even be negative. So we're going to put in a constant amount at the end of each year. We're earning a certain interest rate every year, every month, every day, whatever, every quarter. And the third assumption is that if I put in money every month, I'm going to assume that the interest rate compounds monthly. If I put in an amount at the end of every year, I'm going to assume the interest compounds yearly. And if I put in every quarter, I assume that the interest compounds quarterly. All right, so the interest is going to compound at the same rate that I add to my annuity. That makes sense. So whether that's monthly, yearly, quarterly, whatever. Now, let me explain kind of what's happening with an example. And we're going to do a very simple example. A person is going to put in $1,000 at the end of each year for 3 years. All right. That person is going to gain 5% interest. How much should they have at the end of the 3 years? Does that make sense? Put in $1,000 per year at the end of each of 3 years. So let me $1,000 each year at the end of at the end of 3 years. How much will you have? And again, the interest rate is 5%. Since we're doing this each year, we're going to be compounding yearly. All right. Now, this is a little bit awkward because the way it's phrased, we're putting in the $1,000 at the end of each year. Okay, for 3 years. So if you think about this, I'm going to try to do this on a number line. So my first $1,000 is going in at the end of year 1. That makes sense? My second $1,000 is going to go in at the end of year 2. And then my third $1,000 goes in at the end of year 3. Wrote the wrong number there. Does that make sense? This is what an annuity does. It just puts in, and then the next year it puts in the same, and then the next year it puts in the same. And you can do this over and over and over. Now, if I'm going to calculate how much I have at the end of 3 years, with the tools we have right now, what we would have to do is we'd have to say, well, the first $1,000 earns this amount at the end of 3 years. 1,001 plus R, which is 0.05, over M, which is 1. And notice that if we put in the $1,000, it's earning interest for 2 years. So the first $1,000 earns 2 years worth of interest. That second $1,000 is only going to yield or earn. That's a better way to say it. So the second $1,000 only earns 1 year's worth of interest. So the second $1,000 earns 1 year worth of interest. T is 1. And the third $1,000 I'll calculate these things in just a second, earns 0 years worth of interest. Now you can either put that in the formula or just say that third $1,000 is going to get you $1,000, right? When you do an exponent of 0, it turns out to be 1. So 1 times 1,000 becomes 1,000. So that first $1,000 yields $1,102.50. That second $1,000 earns $1,050. And the third $1,000 is just $1,000, right? So if I look at the total amount after 3 years, the total amount, actually, let me just write total equals, that's gonna be easier, is a sum of those 3 values. Take 1,102.50 plus 1,050 plus 1,000. I ended up with a total amount of $3,152.50. Does that make sense? Yeah.
Why is the first year 2 instead of 1?
Well, the first year, the first $1,000 you mean?
Yeah.
Yeah, so the first $1,000 gets, remember, we have a 3-year period. This $1,000 that I put in blue is going to sit in the account until the end. So this $1,000 is going to gain interest for the total of 2 years. The $1,000 gains interest for a total of 1 year. And then that $1,000 is just not gaining any interest because we did that. I don't know if that makes sense, but yeah. And if we had a 4th year and we added another $1,000, well, then everything, all of these exponents would go up from 2 to 3, 1 to 2, 0 to 1, and then we add another $1,000, right? Now, you can see, hopefully, that this approach, where we take lots and lots of lump sums and add them up, that's actually going to give me the total value of what we call an annuity. All right. However, that's not a really efficient way to do it, because a lot of times the amount of years is going to be really, really big. And a lot of times when you talk about monthly, well, monthly over 3 years, you put in $100 every month over 3 years, that's like 36 different amounts you've put in. That's a lot of adding up. So what we'd like to do is we'd like to use math. Uh-oh. We got a lot of lag time there. Sorry, in projector. Let's see if I can do this. Yeah, it's better. Yeah. But then it does. All right. There's a lag time on the screen in class. Just not moving around, but it's very good. All right. So, anyways. In general, how we're going to calculate an annuity is it's a sum of a lot of different investments, okay? And each investment, if we did this yearly for 15 years, the first one is going to earn interest for 14 years, second one's going to earn interest for 13, then we're going to earn interest for 12, 11, 10, 9, you guys get the point. It turns out that we have a, quote, shortcut formula in mathematics for adding up lots and lots of things with decreasing exponents. If you have something to the n-1 power plus something to the n-2, all the way down to something to the first power plus 1, then all we have to do is take that something to the nth power minus 1, and then divide by that something minus 1. Well, that's what we're doing with these lump sums. We're adding lots of those things up. If I put some amount, which I'll just signify as P in front of that, then when we add them up, you can just factor out that P. And that'll be fine. And so when we calculate an annuity, that number is the thing inside parentheses. That X value is the 1 plus R over M. And this is our general formula for calculating an annuity. This is something, again, when you go to take the test, when you go to do homework, you should have this formula handy alongside all those other things we mentioned. A equals P times the quantity 1 plus R over M to the N minus 1. That N is actually just M times T. All right. All right. That's how many things we're doing. So 1 plus R over M to the MT minus 1 divided by R over M times, instead of just writing the letter P, because we use P for lump sum, I wrote PMT for payment. That's how much you're putting in each month, or putting in each year, or putting in each week, or each quarter, whatever it happens to be. So this is the formula that we need to have with annuities. Does that make sense? So the general annuities formula is that one. Make sure you have that handy. So let's check this out. A person is going to put away $200 per month at 5% interest. All right? And they're going to do that in an annuity for 10 years. After the 10 years, how much will they have? Everybody get that? So they're going to put away $200 a month at 5% interest for 10 years. I'll show you how to do this on your calculator once we get to that stage, but here we go. A equals your payment 1 plus R over M to the MT minus 1, all divided by R over M. By the way, when you do this, I'll get to that when we put it in the calculator. All right, so payment is $200. We're putting in $200 every month. We're doing 5% interest per month. So the R is going to be 0.05. The M is going to be 12. If we're doing that for 10 years, my T is 10. And then the R over M, I'm gonna get 0.05 divided by 12. Now, what I like to do when I write that down is I like to put parentheses around the 0.05 over 12 so that it reminds me to put parentheses around that when I type it into my calculator. Okay. That work? So this is the general formula. And again, usually what I do when I write this into my calculator is I calculate that out as 120 exponent rather than 12 times 10 is the exponent. So let's put that into our calculator, right? Now I'm gonna put that into the TI-84 first, and then I'll show you how to do it in TI-30. It's the same concept. What we're gonna do is we're gonna start on the interior part of the formula. So I have to start in the parentheses. And in fact, what I do is I start in the numerator of that fraction. So I put parentheses 1 plus 0.05 divided by 12 to the 120th power, and then I subtract 1. Okay, so that's the entire numerator. I'll hit enter. Now don't round this number yet, just leave it alone. What you can do is you can take this answer, and if you just hit the divide button, you can divide by 0.05 over 12. Now, because that 0.05 over 12 is a fraction in the denominator, I have to put in parentheses around the 0.05 over 12, or else it'll miscalculate. And then after, I multiply by 200. And so what we get is that the amount we'll have after 10 years is $31,056 and about 46 cents. All right. So that's what it looks like on the TI-84. It looks nearly identical on the TI-30. We're going to start with 1 plus 0.05 over 12 inside of parentheses to the 120th power. And then I subtract 1. That'll give me my numerator. Then I just hit the divide button. And then in parentheses, I have to put 0.05 divided by 12. Again, these parentheses are very important here. And then I multiply that number by 200. Sure enough, you get the exact same thing, right? But the key thing is that if you are doing this, this denominator has to be in parentheses. Okay. And that's the whole thing. I got this straight looking. $31,056.46. That's what you'll have by putting away $200 for 10 years at 5% interest. That work? Not too bad. Again, the calculation steps, calculate this first, numerator first, divide by your denominator, make sure that denominator is in parentheses, and then multiply by the number out front. That's kind of the orders of operations. I want you to try this example on your own. Put away $2,000 per quarter at 8% interest. And do this for 30 years. How much will you have after 30 years? All right. People are doing pretty well on this, so I'm gonna keep moving. The payment here is going to be $2,000 because we're putting in $2,000 each quarter. 1 plus 0.08 divided by 4 to the 4 times 30th power. And again, when we multiply that, oftentimes what I will do is I will write 120 when I type it into my calculator just to make it easier on myself. 4 times 30 is 120. All right. And then 0.08 divided by 4 is my denominator. And now I type it into the calculator. I type in the numerator first, again, usually using 120 rather than 4 times 30 when I type it in. I don't want to have to rewrite it completely again, so the nice thing about using the whiteboard is you can just erase that, write 120, or you could just use another color. Right, 4 times 30, 120. Uh-oh. Oh, didn't work. See if that one does. Alright, so I got 120 by that way, 4 times 30. So numerator first, once you calculate that, when you're dividing by this denominator, make sure denominator is in parentheses, 0.08 divided by 4 is in parentheses, and then multiply by 2,000. And when it was all said and done, I ended up with an amount after 30 years of $976,516.30. So think about that. By putting in $2,000 each quarter, you end up with almost $1 million at the end of 30 years. Okay. Just under $1 million. So this is how, obviously, people save for retirement and things of that nature. Any questions about this formula, this annuities formula? No. Well, obviously, when you compare the last two examples, example 2 and example 3, the amount we got out in example 2 was like 30,000. The amount we got out in example 3 was nearly $1 million. And the reason was all the standard things. How much is our payment? What's our interest rate? How much time do we get to do this process? And so we're going to take a quick comparison of differing the R's, differing the M's, differing the T's. Does that make sense? Okay. So I want you to try to calculate 2 annuities. One is going to gain 6% monthly, and the person puts away $200 per month. They're going to do this for 7 years at, again, 6% interest. And then the other person is also going to put in monthly. They're going to put in $1,000 per month at 6% interest for 7 years. I want you to go ahead and calculate how much each individual will have at the end of those 7 years. All right. So let's go through both of these examples. I'll start with the 200. We put in $200 a month at 6% interest. Again, that's monthly compounding. The exponent here is going to be 12 times 7, which is 84. I'm not going to write that down this time. And then divide by 0.06 over 12. Again. All right. When I plugged all that in, again, I start here, then I divide in parentheses, and then I multiply by 200. When I did that one, I got $20,814 and about 79 cents. Okay. If we increase our payments by a factor of 5, so from 200 to 1,000 is 5 times as much, right? But we still are going to earn 6% interest monthly for 7 years. Again, 12 times 7 is 84. That's what I type in my calculator. So the amount turned out, when I calculated this, to be $104,073.93 approximately cents. Notice that this amount is precisely 5 times this amount. All right, except for rounding. There might be a penny difference because of rounding or something like that. But that amount in the blue is 5 times this amount. And if you look at how much interest earned, you earned exactly 5 times the interest over here that you did over here. I won't do that calculation right now, but that's the whole thing. All right. Notice that this is exactly the same thing we did and the same result we got when we did a lump sum calculation. That lump sum calculation, if we increased our principal by exactly 5 times, the amount of interest that we earned increased by exactly 5 times. Here, the same thing happens in the annuities. If I increase my payments by a factor of 5, the interest earned increases by a factor of 5 too. Let's do one more example of comparing annuities. But this time we're going to change the interest rate. We're going to go from earning 3% interest compounded monthly to earning 12%. That's a times 4 factor, right? So your interest rate has multiplied by a factor of 4. What's going to happen when we look at those end amounts? And we're going to do this for 20 years. So putting away $400 per month. All right. So, again, people are doing real well on this, so let me keep it moving. We're gonna put in $400. One person puts in $400 per month at 3% interest for 20 years. My X fund's gonna be 12 times 20, which is 240. When I type it into my calculator. We divide by 0.03 over 12 in parentheses. So calculate the numerator, divide by 0.03 over 12, and then multiply by 400. I ended up with $131,320.80. $131,320.80. All right. And the second person also put in $400 a month, but the second person gained 12% interest. So the R was 0.12 over an M of 12. Again, for 20 years, so 12 times 20 or 240 as my exponent. My denominator in this case is 0.12 over 12. When I did all of the calculation, I ended up with $395,000, or $395,702 and about 15 cents. Now, comparing interest gained is a little bit trickier than it was in the lump sum problem. If you think about how much each person put in, let me go and calculate that real quick. How much money did each person put in? Well, they put in $400 per month, right? For 20 years. $400 per month, that's 12 times a year, for 20 years. If you multiply all of those numbers up, technically the person put in $96,000. Okay. Now, this isn't something that I'm super interested in and you calculating. But I want to talk about the difference in the interest gain. So I need to have that $96,000 in the back of my head. If we put in $96,000 total, that means in this first case, when you take 131,320.80 and subtract $96,000, that means this first person gained $35,320.80 in interest. Does that make sense? So they made about $35,000. The second person also put in $96,000. And that person gain, well, this minus 96,000. $299,702.15. Is that right? Notice the difference. We multiplied our interest rate by a factor of 4, but the amount of interest gained was well over that factor of 4. So changing the interest rate, just like it did with the lump sum, caused a bigger change than the factor that we raised the interest rate. Is that okay? Everybody have that written down? Let's get this slide. And that was the same phenomenon we saw with our previous example, the lump sum. Now, I'm not going to go through this example. You can do that on your own if you'd like. But knowing that what we know from the lump sum, if you increase your time that you're putting away money by a factor of 3, how much interest gain are we going to increase by? Well, based on the lump sum, it should be more than a factor of 3, right? So the amount we're going to have at the end, the interest gain is going to be more than a factor of 3 if the time gains by a factor of 3. And so we come away with the same takeaways that we did when we looked at comparison in the lump sum formula. When we're trying to do investing, we want to do it as early as possible. That way we increase the time that we gain interest. We also want to get the best interest rate possible. That increases the R. And then we also want to invest as much as I can afford. That can increase the principal or the payments. Right. So it's identical to what we saw in the first part of this chapter, in the lump sum part. When you're investing, do it as early as possible. When you're investing, get the best interest rate you can. And when you invest, you put away as much as you can, save as much as you can. Right? Any questions about that? Those basics? All right. Now the next couple of sections are bonus sections for this chapter. So these sections you won't have specific problems on. But I want to show you kind of what's going on with how loans and annuities are connected. All right. So here's what we do. All loans are are annuities that, in essence, we pay to the bank. Does that make sense? Let's imagine that I have an annuity. And that annuity is going to pay 5% interest compounded monthly. I'm going to pay $246 each month. So we're going to pay in $246 every month at 5% interest. And we're going to do this for 15 years. Okay. Okay. So let's calculate how much we'll have at the end of 15 years. $246 is the payments. 1 plus 0.05 over 12 to the 12 times 15 minus 1 divided by 0.05 over 12. Twelve times 15, I think that's 180, is that right? Yeah, 180. So that's 180 when I plug that in my calculator. 1 plus 0.05 minus 1. So if this person were to have paid $246 each month, the annuity would be worth $65,753.08 at the end of 15 years. Everybody get that? And so the next question says, what present value gives $65,753.08 after 15 years at 5% interest compounded monthly. All right, this was the other question that was on that slide, essentially. Well, if we set up the present value, remember our present value is set up with our lump sum equation. We're solving for P there. We're saying if I want to have $65,753.08 at 5% interest divided by 12. Again, that'll be 180 when I type it in my calculator. All I have to do is take that $65,753.08 divided by 1 plus 0.05 over 12 to the 180th power. That'll give me my present value, right? We did that last time. I got a present value of $31,107.99. Everybody understand that? So this lump sum of $31,000 would produce a future value of $65,753.08. But also, this annuity where you pay in $246 every month would also produce $65,753.08. Does that make sense? As long as it's the same interest rate and the same time period. Let me write that again in a different way. If one were to start with $31,107.99 in the future, present, future, if I just let the lump sum this is my present value. My amount in the future would be $65,753.08. But that's also the same as if in the annuity, we just kept putting in $246 each month. Everybody get that? So here's how this is all connected to loans. This is the diagram that tells you how loans work. What I call the loan diagram, or what the bank is really doing is trading you a lump sum for your annuity. So what would happen is you would go into the bank and say, I want to borrow $31,107.99. And after some paperwork, they give you that. And you'd say, well, how much do I have to pay every month? They do this calculation and they say, you know what, the annuity that gives me the same ending amount is one where you pay in $246 every month. So what would happen is you'd go ask for a $31,107 $107.99 loan, and they say your monthly payments will be $246. Does that make sense? So this is precisely what banks calculate. Or, you know, they do it this way. They have fancy calculators that they put in all the information and they hit enter, and they probably don't know the mathematics behind it. But this is how loans work. Banks are trading you a present value lump sum for your monthly payments. And the way it works is that the annuity that give you your monthly payment and the lump sum will end up at the same ending amount. Is that all right? Now I'm going to stop here. On Thursday, we'll come in. I'll finish this bonus stuff up. And then we'll talk a little bit more about the test on Thursday too. You have all of the material you need to do all the problems on the test. Again, the bonus stuff is not up yet, but so if you wanted to try the test, take your first attempt before Thursday, feel free to do that. Again, study up by doing the problems that are from the homework. Okay, well, those are the practice problems. All right, other than that, I'll see you Thursday.